I think I had given one very easy question. I mean, questions usually in TIFR, BARC as well as GATE exam. You have to see the question in one particular way. That will be very easy. Okay. I had given one cone. Do you remember? Whose base I have got surface area A. So this is your area vector. Now this is the electric field. Electric field I have taken E0 into some z cap like that. Am I right? And I have taken this one as 30 degree. And what I asked is, suppose that is an ice cream cone. What is the flux through that curved surface area? What is the magnitude, suppose? Because whenever you have open surface, you got two choice, isn't it? Whatever magnitude. Now you have again electric, there is no charge in the region. If there is no charge, can I apply my Gauss law? E bar dot dA bar, that's equal to 0. The main mistake that you do is you will think here itself. What is this one actually? Total flux through the closed surface area. Am I right? Now let me take closed surface area, curved surface along with this planar surface. So that is the net flux. Can I say net flux or total flux? Total flux through the closed surface. That's equal to 0 because there are no charges. Why it is 0? Electric fields are piercing from one side. It is going from other side. Isn't it? Electric fields, they are going into that region from one side. There is no net outward flux at all. Isn't it? Only when that imbalances, you will get net flux, remember. So that's why there is no charge inside. There is no source inside. That's why it is equal to 0. Or you can just use your Gauss theorem. So don't try to do any surface integral. Okay. He has given this area. What is this area? Pi a square. This is pi a square into some n cap. Am I right? Area vector. Area vector equal to pi a square into n cap. This is your electric field direction. Isn't it? Now look at here. This total flux should be equal to 0. Am I right? Total flux including curved surface area and planar surface area equal to 0. Write that total flux as, so pi curved plus pi planar. This is the flux through curved surface area plus flux through planar surface area. Isn't it? It is 0. Isn't it? It is 0. If you write this one and if you just think, then you will get this one. Why? Again, you can split. You can total flux. That's a scalar. You can add like a scalar. Isn't it? Scalars are added like this. Now, so phi curved is equal to minus phi planar. Is that okay? So, whenever you take this total surface integral, you have to take your area vector outward from the region, remember. So, then obviously, so this planar area, it will make area vector, it will make acute angle. This flux will be positive. This flux will be negative. You can see this. Am I right? Look at here. What is that phi planar? Electric field dot area vector. Electric field is E0 into z cap. What is area vector? Pi a square into n cap. What is the angle between them? 30 degree. Angle between them is 30 degree. E0 pi a square cos 30 degrees root 3 by 2. Root 3 by 2. Obviously it is positive. Look at here. Why it is positive? Because if you take area vector outward from the region, am I right? So then here also you have to take area vector like this. Then it is making acute angle with the electric field. Obviously you have to get positive one. So that's why phi curved equal to minus of E0 pi a square root 3 by 2. Okay, think over it. Okay, think over it, how to apply, how to make use of Gauss law. Okay. again, I have asked some more question. Again, now you have to read whatever the comment he has written in the beginning of the Gauss law, okay, in Griffiths. Just read each and every sentence very carefully. I have given one more question. Take a kind of ice cream cone. So put a charge Q here. What is the net flux through the surface? Am I right? Now what will you do? Now let me give the idea here. Try to solve one more question. You have to again, to apply Gauss law, you need closure surface, isn't it? To apply Gauss law, you need closure surface. So now, take a closure surface so that our surface of interest is a symmetric part of that closure surface, isn't it? You can take in any way, logically, but take the closure surface in such a way that our surface of interest is a symmetric part of this closure surface. Now, don't you feel that this surface and this surface will, contribute same flux, or they will have same flux, isn't it? So that is the idea. And the same idea in case of the one more question. One charge had the one of the corner of the cube. What is the flux through that one? What is the flux through edge? Am I right? Keeping that charge at the middle, so generate one symmetric surface so that our surface of interest through which that we are trying to calculate the flux, there should be symmetric part of the total surface so that we can divide. Now look at here, total flux equal to total flux. What is this one? Q by epsilon naught. What is the flux through this one? Half of this one. This is total. Am I right? So this flux, that should be equal to half of pi total. Isn't it? Don't you feel like that? That's a symmetry. Isn't it? This should contribute, this should have taken half of the flux. This should have taken half of the flux. That's why that's equal to half of Q by epsilon naught. That's it. This is how you have to apply Gauss law. And so extend the same idea to that cube and one charge at one of the corner, and that is asked many times. Okay? So you have to take a lot of other cubes so that that charge should be at the center of some symmetric surface, and your surface of interest should be symmetric part of that one. Okay? The same thing is, I have taken one hemispherical bowl, am I right? With the Q here, am I right? So take one more, extend this one. Extend the surface so that your surface of interest is symmetric part of total surface. Apply Gauss law to the total surface. Now this is half of that one, am I right? This will take half of the total flux. That's why again Q by 2 epsilon, isn't it? Flux through this lower surface, this should be Q by 2 epsilon. Okay? So try to do that one. First read out Griffiths carefully. Okay? So his comment carefully, and then try to apply your logic. Okay? Yeah. So problem number 2.10. It was an old question again. So he has taken a cube. He has taken a cube and he placed a charge at one of the corner Q here, and he asked what is the flux through this surface. What is the flux through this surface? So initially, actually, when I saw this question first, I tried to integrate this one. Can you do that one? Too difficult to take the limits, area vector, isn't it? Now look at here, your electric field and area vector, they are not parallel, remember, and electric field strength also varies here throughout this one. Electric field strength varies, isn't it? Area vector is constant, and again, I think electric field and area vector angle also varies, remember, you can't do that one. Again, so he's not expecting that one. Then what is the idea? Before discussing this one, I'll go for my question. I think that was again old CSIR question. I have taken a cone, I placed charge Q here. What is the flux through this cone? Half of Q by epsilon naught. Am I right? Q by epsilon naught, if you take, again, how you got that idea? You extended surface. Am I right? He has given one open surface. So suppose ice cream cone. What he has given? He has given one open surface. And he asked what is the flux through that curved surface. Am I right? So now what you have done, you extended that one symmetrically. That's the best idea. extend that one symmetrically. So that now don't you feel that this cone will share the half of the flux, this cone will share the half of the flux, and according to our Gauss law, E bar dot dA bar, that is a net flux, that is the net, so total flux. So through any closed surface, any shaped closed surface which contains charge Q, isn't it? Q enclosed, charge enclosed, isn't it? Any shape. So we have proved for actually earlier, do you remember, we proved for spherical surface because it was very easy, because our coordinate geometry allowed us to do that one. But we can just reshape our what you call a surface, am I right? We can make the shape of the surface, closed surface, any shape. Only thing that does matter how many charges inside, net charges inside. Why? Again, so number of electric fields will not be generated in edge. Isn't it? That was the idea that I have taken. Why I can reshape that surface? We proved Gauss law for spherical surface. Do you remember? I can reshape that one. Why? Electric fields will not generate at air. Remember, if I do it for, spherical surface, if I reshape that one, so then also net flux will be same. Number of field lines passing through the area, so passing through the surface will be same. Is that okay? That's why again any shape region you can just apply that one. You can apply Gauss law. Is that okay? Now look at here. So this again, this total flux equal to Q by epsilon naught. So if total flux is this one, this will be pi total divided by 2. This should say total divided by 2, isn't it? Total flux, isn't it? So that's why. So flux through this one, that will be total divided by 2. That becomes Q by 2 epsilon naught, isn't it? Now what is the idea? Basic idea is extending our surface symmetrically, or extending our surface in such a way that surface of interest is a symmetric part of total surface. I better say like that. Surface of interest is a symmetric part of total surface. Am I right? So then only you can say this will share half, this will share half. Suppose even if I give like this, Q here, if I give like this, now it exactly looks like ice cream, isn't it? Just forget. Okay, this is a bowl, hemispherical bowl. Now also you may feel little uncomfortable, am I right? Whether this will share same flux as that of this one, but it will share same flux as that of lower one, isn't it? Isn't it? Again, start with this one. If it shares half, this should share half. Are you getting my point? But you will not feel comfortable here. You will not get confidence to say this will share that bowl will share the same flux as that of this cone. Am I right? Because that's not symmetry. That's why you got to take it like this. Yeah, speak up. Yeah, it's not symmetric. You are not confident to say that one. But start with this one. If this is pi total by 2, this should be pi total by 2. Isn't it? But in the first extent, you can't say that one. So that's why it's very better to extend your surface so that your surface of interest is a symmetric part of the total surface. So now no. Look at here. Look at right hand side. No, you can take any shaped ice cream. Is that okay? Gauss law is true. Why? So number of field line passing through the area is same. Am I right? Field lines are generated by this Q. They are not generated by air. That was the idea that I have taken. I can reshape the closed surface. Isn't it? You are not getting that one? We have done for, look at here. Earlier we have done Gauss law for this one. Am I right? Q was placed at the center. We have taken one closed surface. We have shown E bar dot dA bar, spherical surface. This was spherical surface is equal to Q by epsilon naught. That is a statement. Am I right? What is this one? This is the net flux through the closed surface. What is the net flux means? Number of field lines passing through. Net flux is proportional to number of field lines passing through. If I reshape this one without, making this one outside the region, okay? I'm keeping this one inside my region. I'm reshaping my spherical region. So then number of field lines should be same, am I right? Number of field lines passing through the surface should be same. It doesn't matter whether it is sphere or any other shape. Why? Field lines are generated by this one. It is ending at infinity. That's why whatever the shape, it should have passed through that one. Number of field lines passing through the surface, any shape, that is same. So that's why you can take any closed surface, you can apply Gauss law. But why I am taking symmetrically? Because you can say confidently this will share half of the total flux. Is that okay? So that's why you will feel uncomfortable when you take like this actually. Hungry? When you take it like this, you will feel little uncomfortable whether it shares half or not. So this is exactly at the top of the cone, okay? You will feel uncomfortable. But start with this one. If this will share half, this should share half, remember. Okay, wait a second. Yeah. Now, so in this one, now I have again, so have you observed one more thing? I placed Q here. I extended my surface so that Q is at the center of my, total surface. Do you remember? So that you have to make this one at the center of some total surface. How do you do that one? By extending this one again. It's have you drawn the NaCl crystal structure? It is like that. So what shall I do? NaCl crystal structure. Yeah, let me start with this one. Let me try again. Wait a second. It takes some time. Q here, okay? So now I have to extend that one so that this surface becomes symmetric part, one thing, and this should be at the center of those symmetry. Okay? So that's why I'm going to extend this one. I'm going to make it as one more cube. Okay? So one more cube here. So then below, is that okay? Now back side, isn't it? It was 5 marks question in PU chemistry. Yeah, we studied like that, am I right? So our teacher used to come to the board and they used to start with, this is 5 marks question, take this. NaCl crystal structure. Isn't it? So now look at here. Again, you should have that geometrical thinking. Okay. Again, after I think our X-ray diffraction, you may feel a little more comfortable. Okay. Try to do this one. Anyway, we have to draw this one. Again, I'm very clever. So whenever I discuss that X-ray diffraction, I will come up with a projector. Why would I draw all of those crystal structures? Isn't it? Again, not a good diagram. Whatever. Look at here. Now you have to take total 4 plus 4, 8 cubes. Am I right? Now look at here. Each, so how many faces? 6 faces. Am I right? Each face will contribute 1/6. So suppose if you take total flux as 5 total, each face of this cube, because this cube is at the center, it's at the symmetric center of that whole big cube. That's why each face will take 5 total divided by 6 flux. Am I right? Now look at here. So this Q is here. Just take these 4 surface. Okay. So now this total surface, it will contribute. So it will take this total surface. This total surface, it will take 5 total by 6 flux. Am I right? Now look at here. This Q is situated at the symmetric. So it is situated symmetrically above this one. If I draw that one again, it will be like this. Is that okay? This is the center and Q is situated somewhere here. isn't it? I have just drawn this Q and this surface over there. Now look at here. So now this will share 1/6 of the total flux. Now look at here. Since these four surfaces, individual surfaces, they are again symmetrically situated. So then if this whole thing shares 1/4, so each of that one shares by 6 by 4. So that when you add that one, you will get pi total by 6. So totally, each of this one, that means he is asking this part, do you remember? Don't forget this one, he is asking this part. So that will share pi total by 6 by 4, 24. So what is pi total? Q enclosed by epsilon naught divided by 24. That's equal to Q by 24 epsilon naught. Any question? Any question? So this will take total flux divided by 6. Again, in that one, each of these squares, they are symmetrically situated. So about that Q, or Q is symmetrically situated at exactly at the center. So that's why because of symmetry, each of these should contribute equally, isn't it? Then this should be pi total by 6, pi total by 6 by 4, pi total by 6 by 4, so that into 4, you will get pi total by 6, isn't it? Each of these will share this much flux, am I right? By 6 by 4. There is no reason why those fluxes are unequal, isn't it? That's the best way to argue. And we use that kind of argument in mathematics, isn't it? Let us assume that it is not true like that. We start with like that. So similarly, there is no reason why they are unequal. That's why they are equal. Again, we know the reason because of the symmetry again. Reason is symmetry again. Now, this is Q by 24 epsilon naught. This is Q by 24 epsilon naught. Wait a second. And let me ask one more question. Think over it again, or just search for NaCl crystal structure and place your Q at exactly center, and then think over it. Q here, okay? He asked what is the flux through this one, am I right? Let me ask one more question here. What is the flux through this surface? What is the flux through this surface? Why? Cos 90. Yeah. So whenever you have a charge on one of the corner of the plane, remember, or on the plane, then electric field from that charge will graze that plane. It will not puncture that plane. Are you getting my point? You have only one charge, isolated charge, at one of the corner or anywhere on the plane. Electric field from that charge will graze that plane. It will not go into like this, isn't it? Obviously. So now area vector of the plane is perpendicular to electric field. Are you getting my point? That's why here if you take area vector, your electric field, remember electric field, so in the region of this plane is will be on that plane. Remember, it will graze that plane. Electric field will be on that plane. Then area vector will be perpendicular to the plane. So dot product is 0. Is that okay? So that's why flux through this one is 0. Flux through any planar surface which contains charge, that is 0. Only one charge. Don't take dipole. If you take dipole, it may go like this. Electric field may go like this. Okay, I'm taking only one charge. So any of this surface or this surface or this surface which contains that charge Q, any planar surface in that Q which contains that charge Q, flux is 0. Why? So on that plane, electric field will graze that surface. So electric field will be on that surface. Is that okay? And area vector will be perpendicular to the surface, and dot product is 0. Yeah, all the three planes which contains charge Q. Point charge. Assumption is point charge. Is that okay? Again, extend that question, okay? Or write down in your book, that's better. Okay? Write down in your book using pencil. Try to answer that one. What is the flux through other part?
What is the flux
This one? This one? This one? Exact at this point. Now you to talk about flux, you have to talk about area first, isn't it? So flux is defined like this: E dot dA or E dot A. You have to talk about area. Obviously, you will get some flux if you take a small patch of area. Are you arguing that is maximum like that? No. If you take any area which is held perpendicular to this field line, obviously you will get flux. But look at here, this area, this surface that is held parallel to the field line. Or in a reverse way, field lines are parallel to the surface.
At this exact point,
No, yeah, so it does matter what is how you held that plane. If you take small plane, if you held it like this, if you extend that plane, if that plane contains this Q, then obviously those electric fields will be parallel to the plane. Are you getting my point? You are holding the plane here at this point, exactly middle. If you extend that plane, if that plane contains charge Q, then electric field from the charge Q will graze that plane, definitely. It will be on that plane. Again flux equal to 0. If you had that one like this, then definitely flux will be there. Is that okay? So again, electric field, whenever electric field grazes the surface, flux equal to 0. Flux means how many field lines puncturing the surface, going into the surface. You have to think like that. And all of these surfaces are very thin, infinitely thin. That's the assumption. Is that okay? Yeah, speak up. It does matter how you held that one, definitely. Is that okay? But here this plane or this plane or this plane, those are in such a way that charge Q is on that plane, okay? So that's why electric field from that charge will graze that one, definitely. Now, we got E bar dot dA bar. Actually, I need some more ideas, okay? Q enclosed by epsilon naught, am I right? That was our general Gauss law. Q enclosed means net charge enclosed by this surface. This is the closed surface integral. Now, can I use my Gauss theorem to convert? What is that one? Volume integral. What is that volume? Volume within this surface. Or we have done ulta. We have started with volume integral and we defined the surface which covers that volume. Am I right? So from here to here, what is this volume? Volume inside this surface. Is that okay? Volume integral of del dot E d2 throughout that volume. That volume is the region inside. That volume is the volume which is the region inside this surface, isn't it? So now 1 by epsilon naught. What we write here, enclosed charge, we can write again volume integral of charge density d2. Charge density means charge per unit volume into volume. We are integrating throughout the same volume. Isn't it? Q enclosed. What do you mean by that one? Charge enclosed by the surface, isn't it? That can be done in this way also. Charge density, so throughout the region, integrate that one throughout the region. Volume integrate that one throughout the region, isn't it? Now these two volumes should be same, isn't it? These two volumes should be same. When those two volumes are same, you can write del dot E is equal to rho by epsilon naught. That is your differential form of Gauss law. Okay. Now try problem number 2.9 in Cartesian coordinate. In spherical polar coordinate, that's still simpler, but try to do in Cartesian coordinate. Now this is one of the way, okay? Now you can start with your, let me do it tomorrow, okay? You can start with your electric field at some point, that is 1 by 4 pi epsilon naught. Any idea? Rho of r prime, d tau prime. Am I right? I think I have written this one. Just revise. R square into r cap. I can start with that one. I can take divergence of this one. Let me do it tomorrow. And I can show del dot E is equal to again rho by epsilon naught. Is that okay? So actually, we got one problem. Do you remember how to draw the vector field? We better start with this one because Coulomb's law was the first input. Coulomb's law and principle of superposition, those were, whenever you write integral symbol, how did you write integral symbol? That was our principle of superposition. You have taken individual electric field due to small charges, you added them vectorially. That is written in terms of integral symbol. Is that okay? So Coulomb's law and superposition principle was the basic input, remember. Now I have to actually start with this one in my actual theory. Then I have to show this one. Then I have to show this one. Del dot E is equal to rho by epsilon naught. I have to first show this one. After that, I have to apply Gauss theorem. Then I better to go for integral form. That's the best idea. Is that okay? Then I can draw the vector field. Isn't it? I can draw the vector field. If I start from here again, you can't. It may not be possible to draw the vector field. Okay? Yeah, we shall do it tomorrow. Now again. So along with those questions, just read out each and every sentence in this Gauss law explanation, okay? Each and every sentence. And tomorrow we shall do application of Gauss law. First we shall do some coordinate geometry, then we shall go for application of Gauss law. 1 second. Yeah, he's asking our earlier problem, if Q is not at the origin or somewhere else, okay? Whatever the problem, if you want to explore Gauss law, your surface or your charge should be situated symmetrically over the surface, or you have to run the surface symmetrically about the charge. Are you getting the sentence? Either you have to run the surface symmetrically about the charge, or charge should be situated symmetrically about the surface, about the total closed surface. Then only Gauss law is useful. Okay? So after a couple of class again, so try to think over it, how we can explore Gauss law. If that surface is very arbitrary, then we can't explore Gauss law, remember. Is that okay? We can't explore Gauss law. Only when that surface is symmetric, when that closed surface is symmetrically situated about that charge, then only we can apply Gauss law. Okay? The same thing will be there. I mean, the same idea will be extended while finding electric field from Gauss law. Isn't it? He says, according to his word, electric field is buried inside the integral. Electric field is buried inside the integral. You have to take it outside. Am I right? How do you take electric field outside? What is that one? Surface integral. You have to run the surface in such a way that along the surface, this is when something will come out of the integral when that is constant throughout the integral. So now you have to run your surface in such a way that throughout the surface, this modulus or mod of this electric field is constant. And again, you have cos theta here, am I right? That cos theta should be also constant. You can't make cos theta constant, you can make cos theta 0 always. Okay? Because you are running the surface, am I right? Closed surface. That's why we have to choose this, if we are able to choose the surface so that electric field, mod of electric field is constant throughout the surface. And again, so I better write it like this actually. I better write it like this. What is this one? Integral of mod E, mod dA cos theta. Am I right? Can I write like this? Now look at here. If this again, if this electric field is constant throughout the surface, I can take out of the integral. Again, if cos theta is also constant, I can take out of the integral. and I can just do area integral. That's our total area of the surface. And in that case, that electric field comes out, isn't it? We can use Gauss law to find electric field. That's why Gauss law, Gauss law statement is always true. But it is useful only in some symmetry cases to find the electric field. Is that okay? So the main aim, main application of the Gauss law is to find the electric field actually. Is that okay? But so only symmetry will allow to take that electric field outside. Think over it, okay? So the similar thing, similar idea we followed here, isn't it? We run our surface symmetrically about the charge so that we can find the fraction of the flux. Otherwise it would never possible. Is that okay? So now here again our next extension is, again we have to run our surface, okay? We call it as Gaussian surface, which is symmetrically runs over the, about the charge, so that throughout that surface our electric field is constant. We can take this one outside and using Gauss law, without going into this formula, without going into integration formula, using that Gauss law, we can find the electric field. That's the next idea. Okay, we shall do it tomorrow. Again, read out all those Stokes theorem and Gauss theorem again, okay, and interpretation.